Yeah, before I start, sir, I'd like to mention, yeah, it's been a great privilege to be in Melbourne for actually already quite some time. I came here to visit first the philosophy department at Monash to work with Ali Ripley, who used to be my postdoc in Paris 15 years ago. We have a long record of collaboration. Ellie and I on vagueness and logic, and there's a network called the let's say Plexus network, which is actually
Don't worry, I think Elizabeth.
okay, great, thanks. It's sort of a lecturer's impulse to check what's going on here. But yeah, basically the this network is connecting several centers, including Monash and Paris and Italy and the Netherlands and the US and even Argentina on topics connected to logic. And my coming here sort of opened new doors, in particular the Crossing door. So Crossing is the lab that was mentioned by Merrick in Adelaide. And thanks to Crossing, I came to visit the electrical engineering department here. It's been very, very rewarding and interesting. And so the talk is today about vagueness and informativity. There's a bit of an oxymoron, right, in the title, because vagueness is another name for uncertainty. Informativity, in a way, is sort of the opposite. I should right away say that this presentation is based on a series of joint works with several collaborators. Benjamin Spector, who's a linguist at École Normale Supérieure in Paris. Adèle Mortier, who just graduated from MIT Linguistics, who used to be our master's student in Paris. And Stephen Verheyen from Rotterdam, who's well known to some of you, particularly to Simon here, and who's a psychologist. And we work together on the topic of vagueness. And as I said, vagueness is another name for uncertainty. But I'm interested in this talk, particularly in lexical vagueness. And vagueness in language concerns, let's say, expressions that fail to draw a determinate boundary of application. So if you compare, let's say, expressions like tall, around, and rich with alternative ways in which we could be more precise in language. So John is tall is vague compared to John is 183 centimeters tall. There were around 70 people at the party. Doesn't tell you how many people there were at the party, unlike there were 73 people. Mary's rich doesn't really tell you what Mary's assets are or what Mary's income is. And like Mary makes, let's say, 300,000 euros a year. And the problem that this talk addresses is really what makes vague language so pervasive. What makes vagueness or vague expression so pervasive in ordinary language across, all of the spoken languages of the world. In fact, it's an old problem. The problem, let's say, interest for vagueness, the very notion of vagueness was identified a very long time ago by the ancient Greeks. It has preoccupied some prominent thinkers and pioneers of modern logic and statistical reasoning. I'm just presenting three pictures taken at about the same time. Here you see Charles Peirce, Émile Borel, and Bertrand Russell. They had very different interests. Russell was not so interested in statistical reasoning, unlike Peirce and Borel. But it's about, let's say, pictures around 1900. In fact, Borel is one of my intellectual heroes because Borel published a nifty paper in a journal he created with his wife, Camille Marbeau, who was a very famous novelist around that time in France, called La Revue du Mois, and he published this paper, An Economic Paradox, the Sophism of the Heap of Wheat and Statistical Truth, which is really interesting about lexical meaning. I published a translation into English about 10 years ago in Erkenntnis, if you're interested. But basically, that paper addresses a number of issues having to do with lexical vagueness, but also vagueness in the practical domain. Now, Borel doesn't really ask the question I'm asking here. Why is vagueness or why is vague language useful, or how is it, useful at all? But Russell asked the question in a paper from 1923 entitled Vagueness. And there's also a very interesting characterization, this idea that an expression is vague, or when we talk of a vague expression, there's a one-many relation between that expression and its meaning. So take tall, for instance. You can think, well, tall it's the expression itself, it maps to several precise meanings. So tall means taller than a cutoff, and it could mean taller than 180 or 85 centimeters. There's of course there's a continuum of, let's say, thresholds you could pick out. And in a scientific language, that that ambiguity, let's say, which is sometimes another way of characterizing vagueness, is eliminated at all. But in ordinary language, it appears to serve some useful epistemic and communicative purposes. And the general perspective of that talk and that research we've been conducting is to model communicative exchanges involving either vague or precise sentences and explain, rationalize in a way, the vagueness of certain words. And that's actually, some people from actually other communities have done it. Like Bart Lippmann has a paper that's been out for 15 years. It's now forthcoming in a journal. He's an economist, a game theorist, and he's asking the same question: why is language vague? Rohit Parikh, in linguistics and philosophy, is a computer scientist and philosopher. Made some suggestions more than 30 years ago, and we are taking a different approach, but we start from a shared intuition, which is that vagueness can be useful in situations of uncertainty. Russell said, vague belief has a much better chance of being true than a precise one. Joanna Channel, vagueness may be used as a safeguard against being later shown to be wrong. And Kees van Dinter, you go to the doctor, if they're uncertain how the future will turn out, they route their predictions in vagueness. So the idea there is that there is a link between using vague language and minimizing error or minimizing commitment. But interestingly, they do not distinguish between, for an expression to be vague semantically, I will explain that, as a matter of the truth conditions of the expressions, and using an expression which could actually be semantically very precise, but just logically very weak. And I'll explain the distinction. So the main perspective of the talk is to show that vague words, the use of vague words can be optimal in situations in which the speaker is actually imperfectly informed about the world, is being cooperative, relative to alternative ways of communicating, which would be more precise. And also, vagueness would optimize a trade-off between being truthful and being informative. And the leading idea, which I think will be of interest to this department, knowing your interest for Bayesian modeling in general, is that we can show how semantic vagueness, which will represent by this idea of the underspecification of a semantic parameter in the meaning of expressions, can be pragmatically recruited to communicate probabilistic information using a Bayesian model of interpretation. So that's really is the sort of main program. And this is something that we've incorporated into a model of interactive language, the Rational Speech Act framework that Noah Goodman and Schulmiller, and also Lester and Goodman have promoted in the case of vagueness particularly. I won't do that because I'm not good at it. The one who's really good at it is my collaborator, Benjamin Spector. But I'll tell you where this becomes relevant if you're interested and where to find out about it. Okay, so I'll start by giving an overview of the theory, and then the end of the talk will really be about the experimental tests we've conducted, and that Adèle Mortier in particular has been doing the heavy lifting for. So imagine a situation in which an agent attends a party, but could not keep track of the precise number of attendees, much like me in front of you guys in this room. I can't really say how many people you are. But if the question asks, if I'm challenged with the question, how many people are there in the room or where they are at the party, what I suddenly do is I have a probability distribution over the possible values of that number. Let's assume for simplicity that the support, so the non-zero values of my probability distribution really lie between 40 and 100. And let's say that 80% of my probability mass is between 60 and 80. So what can I do? How can I communicate that epistemic state? To think about this problem, it's useful to go back to Paul Grice, who was a philosopher of language and maybe most influential philosopher in the field of pragmatics, who distinguished, he laid out a number of maxims about cooperative communication. One is quality, say what you believe is true, and that for which you have adequate evidence. Another was quantity, be informative, and the third one, there's a fourth, but let's look at the third manner, be concise, be orderly. So if you are in that situation and if you're asked this question, how many people, suppose you answer exactly, let's say 63. Well, given the picture I gave here, it might be true actually, but you would violate the maximum of quality because either you say something false or you say something true, but you say something true just by chance, by luck, right? So you don't really have adequate evidence for it. It's too strong. You could just communicate the support of your probability distribution. In this case, quality is going to be satisfied if you say between 40 and 100. But there's an intuitive sense in which you fail to be informative about the shape of that distribution, right? Because for a given support, right, you have plenty of probability distributions which have different shapes, but they all have positive probability exactly between 40 and 100. And so in a way, you're not really complying with the maximum of quantity, although what I say here is not really precise, but I'm going to try and make it more precise. You could try to narrow this down, say between 60 and 80, because you think, well, you think most of the probability mass is there. This assumes, right, that you might even introspect what your probability distribution is. Let's grant that assumption. But in this case, you violate possibly equality again, because it might turn out, that the actual number of people is, let's say, 59 or 83. And the best then, I think in the end, would be say, well, I'm 80% confident that between 60 and 80 people attended. But it's a mouthful. It's actually harder to say, to articulate. It's also practically hard to really ascertain, although I assume that you're introspecting yourself. But let's say you're flouting something like the maximum of manner, right? If you say this. So you see where I'm getting at. The idea is if you end up saying around 70, I think there's the intuition which really got this paper and this project started. And actually, Stephen and I were in my office in Paris, was exactly that intuition. I told Stephen, I think if you say around 70, you check all the marks because you don't say anything. Even if it turned out that it were, 53 people, you haven't really lied. You haven't said anything false. But you still seem to steer the audience to something that says something about your probability distribution, and yet you don't have to say something as cumbersome as the exact description of your probability distribution. So in a way, this is really the sort of gist of the talk today. The rest is really sort of filling in the details. And now I'm going to say what the main sort of statement in our paper is. So that's a paper that appeared in Linguistics and Philosophy in 2023. we don't really state things that concisely in the paper. But the main claim is we show that for some, if there's a common prior distribution between a speaker and a listener on states of the world, in this case, the possible number of attendees in the other party, and the speaker makes a private observation, so something that the listener doesn't have yet, then there exists a vague message, M, such that using that message will provide the listener more information about the variable of interest, namely the number of people at the party, than would any more precise alternative M prime message compared to the vague message M. In other words, there's a sense there will be cases in which using a vague message is going to be more informative than using any more precise alternative. And that's what we claim, and that's why we try to show, and because this is a very complex statement, I'm going to break it down into pieces. First, I need to give a definition of vagueness. I've already hinted at it, but the punchline is that an expression is vague if it has open truth conditions as opposed to closed truth conditions. Then I need an account of what a listener does when they process a message. And there we need an account of sort of the idea of linguistic update. That's where we're going to use a Bayesian model of interpretation. We need this idea that a message can be more informative than another. And there we're going to use this notion of Quillback-Leibler divergence to measure informativity. And finally, we need an account of lexical alternatives. We need to contrast vague and precise expressions, and as I will explain, for instance, we don't include explicit probabilistic talk in that model. So that's a limit of our account. But I'll explain that. Okay, so that's the overview of the theory. Now I'm going to the part that is about modeling the listener. Then we'll model the speaker, and then we'll test the theory. So let's focus on my favorite vague word, which is around. So if you say X, let's say the number of X is the number of people in this room, let's say, is around, let's say 20. What do we mean by around? So there comes the logician in me. And the idea is, well, we say that this number belongs to an interval. The interval is centered on 20, so n is 20. But it's an open interval. So we have this variable y, which you can think of as a random variable. And we say it could be any interval of the form n minus y, n plus y. So 20 minus 1, 20 plus 1, minus 2 plus 2, and so on and so forth. Okay. On the other hand, if you have an expression like between is a precise expression because you have to specify the upper bound and the lower bound. So if you say x is between, let's say, 20 and 30, really you say x belongs to this interval going from 20 to 30 included. Yes, of course, yeah.
So your definition of vagueness, let's say person said party, but in a way it's vague. It can be tea party, can be any kind of party.
Yeah.
So would it satisfy the definition of vagueness because it's open-ended? The truth.
Yes, it would, but it would be so here I'm setting aside the vagueness that there might be in other words of the sentence. Like party is a vague word, you're right. And I have more to say about the vagueness of, let's say, nouns, common nouns like party or table or chair. But you're absolutely right. Vagueness is really pervasive, and you're challenging me to say what would be the way of modeling the meaning of a noun like party. here I'm actually making the task easier, because for a word like around, it's vague, but its vagueness lies probably along a single dimension. For party, there's multidimensionality, and I'm setting that aside for now. So you have to get me back during the Q&A, and then I can say more about multidimensionality. But for now, I'm going to focus on vague words, which you can think of as one-dimensional. And for instance, so there's a mapping, in other words, in this case of around to just a number line, right? For party, it's probably much more complex, and I'm not going to deal with that as a first pass. But that's an excellent question. Thanks. And what I want to focus here is just on the contrast between what I call closed expressions. You see there's no random variable here in the meaning of around, whereas there's one in the meaning of between, but there's one in the meaning of around. And I'll show more examples. I'll show one more example of that, but that'll suffice to sort of get the message, I think, through. So now we want to model the listener. So we represent the listener's information state by a joint probability distribution over these two possible values. Remember, we're interested in the number of people at the party. The number is X. It's also a random variable. And there's this other random variable, which is part of the meaning of around. And believe me or not, but it took us a long time to clarify that distinction. This idea that really you have a probability distribution on the value on the number of people that there might be in this room, let's say. That's really a probability on the world as it were, namely the size of a crowd, of a crowd. And there is another random variable, which is the size of the interval denoted by the word around. That's the probability relative to meaning, right? To language. In other words, you have this expresses uncertainty about language. This expresses uncertainty about the world, and we want to combine both, into a model of communication. That distinction is not made in the philosophical literature. I mean, I don't want to, let's say, start a long speech now about this, but I'll get back to this. And we assume that these two prior probabilities are independent. So in general, we assume that the joint probability, right, the probability on X being equal to K and Y equal to I, is just a product of these two probabilities. So they are independent. And now we can model listener's inference. The listener's problem is to figure out what is the value, the number of people at the party. Now that I hear that this number is around, let's say 20. So really, we have to calculate the posterior of that value, given that X belongs to this open interval, n minus Y, n plus Y. And what we can prove is that given this uncertainty about meaning, about the parameter Y, the closer actually the value X is to the target number n, 20, right, the more likely it is to lie in this interval. So in fact, what will happen is that the probability of values closer to the number expressed in around n will be increased in the posterior compared to the more remote values. I'm not going to, you can derive that formally, so you can calculate this posterior very explicitly. I'm not going to do this, but I'm going to show you what it would look like. Imagine you have a flat prior on the number of people that there might be in the room in an interval going from 0 to 40, right? What you hear around 20. So the largest interval in principle would be, 20 minus 20 or 20 plus 20. I'm assuming that these intervals are symmetric. Of course, you might challenge that too, but let's assume that. And I'm also assuming a flat prior on the meaning parameter, what is the size of the interval. So in red, what you see here is the flat prior on the variable of interest, the number of people at the party. And if you hear there were between 10 and 30 people, what you do is you get this blue posterior, right? You eliminate the values outside of the range, and you normalize. So you get a flat posterior starting from a flat prior. What is really interesting is that with a round, given the calculations that you can make, you won't get a flat posterior, you get a triangular posterior in this case. And as you see, the value, the middle value, the target value is the one that gets the largest posterior probability, and then it sort of smoothly decreases. But even the most extreme values, they get a non-zero probability, which models this idea that if you say around, you still sort of safeguard against, very against extreme error in this case. So that's an interesting contrast. And you might say, okay, but what happens if your priors were arbitrary to begin with, right? They may not be flat. You may have an idea, about people coming to a party, or people being in the room here. So the more robust fact that we can prove is, irrespective of the prior, if you take two values, K1 and K2, and K1 is less than K2, so take a value x equal to n minus K1. So because K1 is smaller than K2, this one will be closer to the target number. So for instance, if K1 is 3, you would say x is 17, and if K2 is 5, it would be 15, right? So you can show that the ratio of the posteriors for around is going to be larger than the ratio you had for the priors. So for instance, the prior you had for the number of people being 17 compared to the number of people, being 17 compared to it being 15. Look at this ratio, and now look at the ratio of the posteriors when you hear around. This ratio is going to be increased. Why? Just in the same way it is for the flat priors, right? Because as you see, the value of the probability for, let's say, 17 is larger than what it is for 16. And it would happen the same way, all the same, if you had a very different prior to begin with. And remember that for between, right, we basically keep the same shape for the posteriors than we have for the priors, because we just renormalize, we eliminate. And so it means that the ratio of the posteriors for around is also going to be larger compared to the ratio of the posteriors for between expressions. And that's what we're going to test eventually. If you want to picture another way of representing this, look at all the intervals, right, centered on the target value n. They're all symmetric, and pick a value k which is closer to n than k prime. And what you see is that k will belong to more of these centered intervals than those k prime, right? So intuitively, it will get more of the posterior mass of your probability than k prime. Yes, Andy.
So I'm thinking of something that seems like it's an exception, which tells me either I'm missing something or I'm thinking in a way that isn't covered by your. So what I'm thinking of is, it feels like the number they choose also communicates something. So for instance, if I said around 22 versus around 20, me using a more precise number is indicative of having a smaller standard deviation around my uncertainty. And if that's the case, then I think you might end up with a case where, say, if I said around 22, then 30 is going to be more unlikely than if I said around 20.
Yeah,
because of that.
that's
And
right.
So yeah, am I missing?
No, you're not missing. It's just that there is an interaction here with, let's say, around and the status of numbers, of target numbers, whether they themselves are round numbers or non-round numbers. And on what I'm presenting here, we don't take that element of complexity into account, but that's absolutely right. And you're absolutely right that there are what's sometimes called granularity effects, and they're not represented here. So we're assuming that, yeah, we're assuming something like the larger the number, the larger the span of the values triggered by a round. And that's an idealization which is empirically disproved by your intuition and actual examples. You're absolutely right. So
That's fine. I mean, you can think of it as you're just looking at a round and I'm looking at the round plus the number chosen.
yes, that's right. Or you could think we're keeping a sort of we're setting the granularity fixed. In my examples, for instance, or in more examples you're going to see, I'm happy to go by multiples of 10. And well, maybe at least on a given range that will solve the problem or eliminate the problem. Thanks, but that's a very legitimate question. So let me just end that part in saying that around, as you see, around end encapsulates a multiplicity of more precise between M and M prime statements. That's very clear from the meaning of that expression. But the Bayesian effect of that multiplicity on the listener differs from the individual effects of each of these more precise statements. That's sort of the interesting aspect of the modeling here. And the claim we make is that this property holds more generally of semantically vague expressions relative to semantically precise expressions. By the way, precision in language may be more of an exception than than the opposite. But we can talk more about that in the discussion. Now comes the speaker side. So as I said, the speaker is in a situation of making a private observation that the listener hasn't made. That's the point of communication. And the idea, let's assume the speaker makes an observation which has support 10 to 20 and is biased towards central values. So the idea is that it might be more informative to say around 15 than to say between 10 and 20, even if actually the around 15 sentence does not in fact rule out some of the values that fall out of that interval. So that's a slightly counterintuitive aspect that I'm going to explain. And the idea, again, is because around 15 in this case will result in a posterior distribution on the listener side, which will be closer to the speaker's observational distribution than the other competing, let's say, distribution. So this is where we need a notion of probabilistic informativity. So we view the speaker as aiming to bring the listener's distribution over the value of interest as close as possible to her distribution. So we need for that to measure how well a distribution approximates another one. And this may be familiar to some of you. It wasn't actually to me when I started this project. I learned a lot from my collaborator, Benjamin. And I'm going to walk you through the same steps. So I hope it'll be useful. So at some point in time, listener and speaker have the same distribution over the value of interest. Then the speaker makes a private observation. And the listener made no observation. This is common knowledge. Then the speaker chooses a message, and the choice is governed by the decision I mentioned, bring the listener's distribution close to one's own. So we have this common prior distribution initially. The speaker's observational distribution I'm going to call P sub O, and the listener's after hearing the message, peace of them. Okay. Now, the speaker, when making an observation, can be more or less surprised by the observation. And as you know very well, we can model this notion of surprisal using this logarithm, negative logarithm on the probability of the value being, let's say, this number. And the same thing for the listener, right? Except that the surprisal will be on the probability distribution based on the message heard, okay? So just a simple example, if the speaker is fully informed, she will not be surprised at all when observing, let's say, 20 people. So the surprisal, the probability then would be 1, and the surprisal would be 0, right? So far, so good? Okay. Now, the goal of the speaker is to minimize the difference in surprisal between the speaker's value and the listener's value after they learned that value. But the speaker, as I assume, is actually uncertain about the value of interest. So the best the speaker can do is to minimize the average difference between the listener's future surprisal and their own surprisal if they learn the true value, okay? So we start from this idea that there's a difference between the listener surprisal and the speaker surprisal. We can rewrite this into this expression, right, which is the flip signs. And now we calculate the expectation of this difference from the point of view of the speaker. So we're going to basically put weights alongside these differences, and we weigh them by the probabilities of the speaker. And so when you look at this expectation, you can rewrite this into the difference between log is the log of a ratio. And now this expression may be familiar to some of you. It is called the Kullback-Leibler divergence between these two probability distributions. Yeah, sometimes it's written this way, Kullback-Leibler divergence between the speaker's observational distribution and the speaker's message distribution. And the strategy of the speaker is actually to choose a message which will minimize this divergence, okay? So you can think of this divergence as a notion of cost that's attached to a message. And note that if the listener's distribution assigns 0 to a value to which the speaker would not assign a 0 or would not rule out, in this case, the divergence will be infinite. And that's bad because the speaker, as I said, is cooperative and doesn't want the listener to rule out values that the speaker thinks possible. Okay, so that's one of the constraints encapsulated in that notion. So here's an example. I'm going to illustrate it. Don't worry, because it's many numbers. But assume now we have, let's say, multiples of 10, right? We can have 0 people, 10 people, 20, and so on. We have a uniform common prior on these values of people who might be at the party. And the speaker makes an observation which is going to be very heavily biased towards the central value 40, right? And now we can calculate the listener's posterior depending on the message heard. If the message is between 10 and 70, which actually matches the speaker's support, right? Because the speaker actually rules out 0 and rules out 80. We have this flat posterior. But if we do the calculation for around, we will have the kind of peaked posterior which you saw before. But notice that this posterior doesn't give 0 values to the extreme cases. So this is more inclusive than the support of the observation of the speaker. But the interesting point is that if you calculate the Kullback-Leibler divergence for the between message compared to the around message, it is smaller for the around message. So the speaker prefers around. And that's the sense in which this expression is more informative than the precise one. So this is illustrated here. It's clear to see this on this plot. You have a common prior, as you see. This is an artifact, right? You have the posterior for between, and here you have the speaker's observation. You see it's very nicely symmetric around on 40, and that's the posterior distribution for around. And the idea is just that this red distribution approximates or is closer from the Kullback-Leibler perspective to this blue distribution than the green one is. So that's basically the idea. And as I said, now there would be a way of encapsulating this approach into a more sophisticated model, which is that the listener might infer that if the speaker uses that strategy, it's because the speaker expects the listener to think that the speaker does it on purpose. And now this is the rational speech act framework, which has these many layers of let's say a literal listener, and pragmatic listener, and likewise literal speaker and pragmatic speaker, and then there's a series of embeddings. And what Benjamin did beautifully is to embed this model into this hierarchy of levels to show that if you do this, you will increase these effects that I described to you. I won't do it here because I'm really not good at presenting this. I get entangled in the complexity of these levels, so I stop at level 1 myself. Okay, how much time should I speak for? Because I want to show you the data. I've spoken already a fair amount. Another 10 minutes, and then there will be questions.
Let me double check.
Okay. Because I don't want to speak without any questions, so I'm happy to press through the
5 minutes if you want to share questions.
Okay, so I'll just
Checking to see if someone's going to take the lead.
okay, I'll just no, I'll just go quickly through the end of the talk. First, there is an issue, which is how can you generalize this model to other vague expressions? So there's a hypothesis or a thesis, right, which is for every semantically vague expression, you can have the same result. If you're interested, I can show you how it works on toll. So toll is also an expression we can model in terms of this operand parameter as part of its meaning. For instance, toll is less precise than taller than. This is, again, a poor example in which if you start from a flat prior on the heights that people might have, if you say taller than 770, that gives a step function. If you say tall, starting from this flat prior, interestingly, it gives this linear posterior, but note that it means that the taller value will be more likely than the shorter ones. Very plausible way of representing the effect of hearing toll on a listener. And again, if you calculate this is the observation of a speaker. However imperfect this red line is compared to the blue line, it actually has a Kullback-Leibler divergence, which is better, shorter or smaller, sorry, than the one for the green line. And Well, the reason is just that this one would rule out, it would give you infinite penalty, and that's bad. A more realistic case, but I'm not going to go through that. So I'm going to finish on testing the theory. We basically tested the theory experimentally. We did a series of experiments. I'm just going to present the last one we did. We tried to elicit probabilities for these expressions like around and their precise counterparts. So we look at how people interpret around n, for n being 40, 50, or 60. In examples like this. So Peter was at Mary's party. He doesn't know exactly how many people there were. He says there were around 40 people. And we asked people to select an interval first. Where do you think the true value might lie? And then we ask people to do a probability estimation task. So we return the interval selected, and we say, well, just move the cursor to say, we don't even have a precise value. We just have them intuitively. How would you move the slider to give you the idea of how probable the value is? And we do it for between as well, right? We do the same probability task. And what we want to measure is basically the ratio I told you about, right? This ratio inequality, remember, we assume that the ratio of the posterior for values closer to n are going to be larger than for values closer, for values more remote. We have some stipulations. I don't have the time to really go into this. I'm going to show you just the results, sorry. Is that in our third experiment, we just represent this histogram basically tells us over these participants we have over 250 participants. A majority of them have this larger ratio for around than they have for between, right? And we robustly confirm this across experiments. And this is what you see for the group data for the different cases. As you see, we get basically the more peakedness for around than we see for between. Okay, so I'm going to conclude. What are vague words on our account? They contain these, they are open meaning expressions. And in a way, vague words help us to basically communicate uncertainty in a way that is more faithful to our perceptual or observational uncertainty than communicating with precise expressions. Not always, but in some contexts, right? And we found some experimental support for this hypothesis. So question asked how to generalize this to multidimensional vague expressions and other questions, but I'll let you ask these questions. I want to finish here. Thank you very much. There are some refs if you're interested. Yes, you were first, I think.
Yeah, thanks. This is really, really cool.
Thank you.
I have many questions about this, but one thing I was wondering is how much of this depends on the shapes of the distributions? Because if this is maybe me misunderstanding things as well, but it seems that you often assume uniform distributions.
Yes.
Most of these things, but say like there's a uniform or flat distribution for between, whereas you might say that someone assumes a different kind of like a normal distribution.
Yeah, absolutely.
Between, say, just the fact that someone said between 10 and 17 means that there's a higher probability assigned to values that are more central or predictable.
Yes.
So how much of this depends on those kind of assumptions?
In fact, it theoretically doesn't. So that's the strength of this ratio inequality, is that, as I said, although I motivated, because analytically it's much simpler to present the example starting from these uniform priors, you may assume any prior and derive the same ratio inequality, meaning that even if you had a U-shaped, let's say, prior, of course, the effect of, let's say, using around compared to the effect of using between would be harder to detect, right? But it would still be present on the just purely theoretical side. Yeah.
That's because there's more vacantness towards the center.
That's because the values closer to the target values are going to receive comparatively more weight than the same values after the message between. And so of course this was also the point of the experiment. Of course, we couldn't actually find people's priors. We haven't looked for people's priors, right? But we just compare the posteriors, but we note that we do this within subjects, right? So we still get some some information, right? We see that when we compare individual by individual, their ratio for around and their ratio for between, although we don't know what the prior is, we see that it's more pronounced in the positive sense than the negative sense.
But on the questions to follow up, so I understand, it does require there to be more density at the measure of central tendency under around. Like the assumption is that by saying around, we're amassing more density towards central tendency. Is that in order to make that?
Yes, that's because that's the effect of, that's part of the meaning of around on our expression. Absolutely.
Yeah.
That's sort of hardwired into the meaning of around. Absolutely. But these are absolutely great questions. Believe me, when I started the project, I hadn't them clarified at all. That was 5 years ago. Thanks. Yes.
Nice about the slide where you're showing the slider results.
Yes. Yeah.
Oh yeah, this one. So as I understood the theory, it was proposing that the meaning of between would be a flat distribution, whereas this one does have some central peak. So why is this not inconsistent with the?
Again, because you might have a prior which already has this a congruent shape, and using between is just gonna, or it might have a different shape outside, but what you do is you reallocate the value of the external values uniformly to your prior in a way that would obey this shape. So this is the same answer. Our model is compatible with arbitrary priors on the.
In what sense is that a prior? Because if you told me between 3,000 and 5,000, it would be a completely different part of the space. So it seems like it's the information about the peak here is coming after I received the message, isn't it?
Well, I think you might deem initially very unlikely that there were so many people, right? But if you're Bayesian, you would just use that information and just shift all of the initial mass you had to that range, let's say. So I don't see anything, let's say, particularly unorthodox from the point of view of Bayesianism here. That's what I'm saying. Maybe I missed something, but happy to talk more about it.
Yeah, I'll see you later.
Yeah.
This is just trying to clarify, maybe from Charles's question. Is the point being that if it doesn't have to be a flat distribution from between, because if people initially had a prior that it was more likely to be, say, 38,
yep.
What could just be happening is that they're just scaling it down from that initial prior. So it just needs to be like less than, it could overall still be a normal distribution, but by saying between, it makes them think it's flatter than it was previously. Is that kind of what?
Remember that between is in principle only ruling out values categorically that are outside of the range, and you take their weight and you just reallocate it to the other range uniformly, just in virtue of Bayes' theorem.
It's the part that doesn't match my intuitions. I think between pragmatically signals that you believe the true value to be somewhere in the middle of the range that you gave, because if I say between 30 and 50, it's signaling I think it's around 40. If I really thought it was around 45, I might have said between 40 and 50, say, or I would have given different endpoints.
Yeah, I have, so that's interesting intuition. I have a different one if I vary the examples. So if I say this room can contain between, let's say, 30 and 50 seats, let's say. In that case, I think I look at the range, or if I say at the party, there will be between, let's say I specify a lower bound and an upper bound. To me, these min and max values can be used to signal that anything can happen over that range. It would be odd to say this room can contain around 40 people, if in that case, let's say, to mean exactly the same thing. So the intuition you have for between, I tend to have it more like by default for around because of such examples. But you're right that we use between consistently with having, let's say, information that already biases or has central tendencies. That's not incompatible with the model. Yes. Oh, sorry, there was one question there first. Sorry.
This might be stuff that you looked at in the sort of higher levels of the theories that you sort of left out, but it feels in my intuition that there are actually quite a lot of cases where having a sort of counterintuitively having a perfectly accurate description and getting someone exactly to the posterior in real world terms will actually be less informative. So you can actually give someone more information, but that would be worse for communication. And like a time you might think of that would be like, if it's sort of like a Chekhov's gun kind of situation. If I said that there were if I went to a party and there were 17 people, because I knew that there were 17 people, I might not say to you that there are 17 people. I might say there were a bunch of people.
Yes.
Because if I say 17, it sort of implies that later on it's going to be relevant somehow. Or like if you said, yesterday I had breakfast at 8:57 a.m. Like I knew that, and it doesn't take that much more to say. And there's lots of times when it doesn't take much more to say the information, but it sort of implies that that information is important in some way or something beyond like, yeah, I don't know.
Thanks, that's a great question. So I haven't talked about relevance. That's a fourth maxim by Grice. But there is a really nice paper by Jean-Baptiste van der Ernst and Dan Sperber, and sorry, I blank on the name of the middle author. Their paper is called by relevance and giving the time, communicating the time, and they have situations exactly like the one described, where people will sometimes, even with digital watches, prefer to, let's say, round off the time instead of communicating what they exactly have on the watch. And I'm not sure that our model captures that, because here we would assume that if the speaker is perfectly informed, the speaker would always choose to give the exact value. So it's a bit like Andy's question about the roundness of the numbers. There are other pragmatic effects that we don't capture with just this model. You're absolutely right.
Let's do one more question.
Yes. I want to query a different part of the model, which is, you said in deriving the KL-divergence as a measure of this, you say, well, the speaker can't know for sure what will happen, so the best they can do is to take an average over, take an expectation.
Yes, yeah.
That's the case for some communicative acts, but it's not the case for others. In some cases, I may prefer people to overestimate than underestimate. Right? If I'm giving financial advice,
yes,
and I say the price of gold tomorrow will be around $4,500 per ounce. If I'm giving that advice, I may prefer to impart a lower bound. The price of gold tomorrow will be at least $4,100 per ounce.
yes.
So the question I'm asking here is this effect that you have where vagueness is more informative. Have you played around with other sorts of preferences over belief states and the circumstances under which that might be the case?
That's also an excellent question. We haven't directly, not with this model. But let's say at about the time that these ideas sort of sprung to me, I was working on a paper on vagueness and lying, the use of lies, how much vagueness could serve to avoid explicit lies in language. And that had to do with more adversarial uses of language. So the example was if you're asked, let's say, how much you paid for some good and you don't want to answer precisely, for instance, how much you bought your flat or your house. And so in that case, let's say you can also have an incentive to be vague. And that assumes that then you're not fully cooperative. You want to hide some information. So it's a bit different from your example. Your example is right now to me a bit more challenging because I have to think of let's say whether our assumption of, as you said, taking the average or the expected value assumes some default epistemic perspective from the speaker, and then I need to think more about that. But those are the kinds of cases I've thought about, but not explicitly. Thanks very much for the question.
Thank you, everyone.
Thanks very much.